Actually, we want to look at some questions from the principle of moment. I'll be taking them from a JAM questions. We have JAM question 2008, question 8 of 2008. It was also repeated in 2016. So JAM repeats some question at time. The diagram above shows a system, a plant that is in equilibrium with this fulcrum O. So we have when the plank will be in equilibrium, we said that with 2p was eventually added here. So what's going to happen? How will the plank return to equilibrium? Is it by moving Q nearer to O? If you move Q nearer to O, we are reducing the anti-clockwise, the clockwise moment. So that's not good for us. If you move the P nearer to O, if you move this P nearer to O, of course at the point will be reached when it will not be in equilibrium. Why? Because this one has been increased, the anti-clockwise moment has been increased. So we need to reduce the anti-clockwise moment to make the system be in equilibrium again. So B is actually our answer. But we can go further and look at C. C adding a weight Q to O. Of course, that's not going to form anything. Any weight added at this fulcrum has got nothing to do on the equilibrium of the system. Moving P further away from O. If we move P further away from O, we are further increasing the anti-clockwise contribution to this system in equilibrium. So that is not an answer. So answer is clearly B, by moving P nearer to O. So quickly go to question 47 of 2007. We have this system is in equilibrium, and we've been asked to find the weight of the meter rule. The weight of the meter rule we ask them through the center of gravity, which is through the point 25 centimeter. So let's quickly get a point 25 centimeter. We have 0, 15 with 200 Newton out through there. 15 we have a fulcrum. We have the meter rule. Let W be the weight of the meter rule. The weight of the rod. Then we have 45. At 45, we have another weight with 40 Newton. Then the end of the meter rule. The end of the rod. So we have what's the weight of our rod? The weight of our rod is our W. We have to choose a moment, the point. We have to choose the point we'll be working with, such that we wouldn't have to deal with so many variables, so many unknowns. If you look at it, we have the reaction here. So the best place we have the reaction up here, reaction from this fulcrum. So it is good for us to take a moment about this point. If you take a moment about any other point, see, we are going to get the answer, but we are going to solve one or two equations. So if you take a moment about this point, we are going to have this is going to be is going to cause clockwise moment. Anti-clockwise moment, anti-clockwise moment. This one is going to cause clockwise moment. This one is also going to cause a clockwise rotation. This one clockwise rotation. So these two clockwise, this one anti-clockwise. So the sum of the anti-clockwise should equal to the sum of the clockwise moment. Or you say the sum of the moments about any point is 0. So 200 times the distance 10 should be equal to this one. The weight multiplied by the distance is 25 minus 15, which is 10, plus 40, 45 minus 15, which is 30. 10 plus 45, 40 times 30. So we have 2,000 equals 10 W plus 1,200. We divide everything by 10. We divide both sides of the equation by 10. We're going to have that. We're going to have 200 equals W plus 120. So at the end of the day, we're going to have 200 minus 120, which is 80 Newton. So the mass of, the weight of the rod is 80 Newton. Thank you very much.